Alright, so I promised that we'd look at mechanisms of addition reactions to alkenes. And the first one I'm going to go through is hydrohalogenation. And depending on what you're used to, this is a fairly simple two-step mechanism, but there is going to be a ton of new information. It takes a little while to get used to the electron arrow pushing, where we show the changes in what the electrons are doing based on what happens during the reaction, and we represent that with arrows. So a hydrohalogenation of an alkene would be we add a hydrohalic acid, fancy names you learn here, like hydroiodic acid. So if you had propene and you added hydrogen iodide or hydroiodic acid, if it's dissolved in water, then it would react to form an iodide. So the first step, as hopefully you would expect, is if you have a very strong acid, that would react with pretty much anything that has an electron pair or some electrons that the strong acid could protonate. So propene, although it's usually not a base, it's going to be forced to be a base in this environment where the very strong acid. So what happens is the pi bond is the source of the basicity. So you can say that the hydroiodic acid, being a very strong acid, is going to protonate the propene, but the way we represent that is the pi electrons in the propene go and fetch the H plus off the hydrogen iodide. And then the bonding electrons between the hydrogen and the iodide end up just on the iodide. So there's the first step in the mechanism written out with the arrow pushing formalism. And when that happens, it can go two different ways. And this is where I said there's going to be a lot of information here. If you have a pi bond, it's being shared between two different carbons, right? So either one of these carbons can get the new hydrogen. And since these carbons are different, if the hydrogen adds to the first carbon or the second carbon, we'll get two different things. So if the hydrogen adds to the first carbon, or the hydrogen adds to the second carbon, they've got two different things going on here. And the other part is when the pi bonds move towards the first carbon to make a bond to the first carbon, it leaves the second carbon electron deficient. So something that's probably useful is I'm doing sort of a skeletal structure here and here so that I don't have to write as much, but it might be really useful to show this kind of step more explicitly with Lewis structures. So the propene, and this is what I would do if you're new to this, I would write mechanisms out showing every atom. It's more tedious, but you're going to make sure you pay more attention to the octet rule, what's attached to what, and the rest of that. But if you have a hydrogen iodide, and in Lewis structures you show every valence electron, so that's going to be important in all the Lewis structures. We're going to say that this pi bond is going to go fetch the hydrogen, and if it does so that these electrons end up associated with the first carbon, then the product will have the new hydrogen. And I should probably use different colors for this. When I'm on the whiteboard at school, I'll always use different colors to represent things. Here's a very subtle change in color, but I'll put the new hydrogen in pen, and that's attached to the first carbon, and now that leaves the second carbon electron deficient. So most of the molecule remains exactly the same. This carbon had two hydrogens, this carbon had one hydrogen, this carbon had three hydrogens. Adding another hydrogen didn't change any of that, but adding this hydrogen, having these pi electrons move over to here to make this bond, leaves this lacking electron density. So this only is making 3 bonds 3 electrons are assigned to this carbon, making it a carbocation. This is a carbocation because when we added a positively charged thing to a neutral molecule, we get something that's overall positive with a formal plus charge on the carbon. So that's going to be really important. So when I go back to our mechanism, this first step was fairly incomplete for a couple reasons. I didn't have the charge on the newly formed carbocation. So if we add the hydrogen to the first carbon, puts a positive charge on the second carbon. And again, that detail is shown here, which is very important. If we put the hydrogen on the second carbon, the electrons move this way, it leaves the positive charge on the first carbon. The other thing is that as we added the hydrogen to the propene, the iodide gets the bonding electrons all to itself. So we're showing the move in the bonding electrons moving towards the iodide. So there we go. It actually becomes an iodide. I've been calling it an iodide, but it before was part of a covalent molecule and didn't have a charge. Now that it gets the bonding electrons all to itself, it becomes an iodide. So there's our carbocation intermediate. So whenever you have a hydrohalogenation, the thing that's in common is the first step is going to be a protonation of the alkene to give a carbocation intermediate. Super important to sort of have that general idea down. What's going to happen first? Protonation of the alkene to give a carbocation, and then you can see the details of how that happens. Now the carbocation, we talked about earlier, what's a primary carbon versus a secondary carbon versus a tertiary carbon. And this is part of why we talked about that. Because here we have a primary carbocation. This carbon with the positive charge is only attached to one other carbon. That's a primary carbocation. And that's not very stable. The positive charge needs more electrons around it. And being isolated here at the end, it doesn't have the bonding as many bonding electrons near it. So the primary carbocation is a higher energy constitutional isomer of this carbocation, and that means it's going to form less often, and this is going to be called the minor intermediate. Now this carbon is attached to 2 other carbons, and so this is a secondary carbocation. And that's much more stable and favorable than a primary carbocation. So this will be the major intermediate. So this will form more often, and it depends on the details of the reaction conditions and everything else, how much more of this you get than this. Sometimes it's like 99% to 1%, sometimes it's 56% to 44%. It all depends on the details, but you're definitely going to get more of the secondary carbocation than the primary carbocation. So that's the first step. Again, a lot of new information. Once you have the carbocations and the iodides, you're going to have a nucleophilic addition kind of reaction. And I'm just going to draw the pure skeletal structures of the intermediates here. Over here I showed where the new hydrogen was going, but we just know it's there now. So secondary carbocation, we got a positive charge, a carbon that's not obeying the octet rule. It is totally set up for something with electrons to bond to this. And there's our something with electrons. So the iodide, so use its lone pair to come in, and this lone pair is going to become a bonding pair. So like in the first step, bonding pairs become lone pairs. That's very common in these mechanisms.